Hi guys. Okay, so in this video, we are looking at the learning check problems from chapter 5 Thermochemistry in the OpenStax book, which is the chemistry second edition. Okay, so we will cover the learning check problems 5.4, 5.5, 5.6, and 5.7. So let's get to the first problem, which is 5.4, and this problem is on page 247. Okay, so here the problem reads as 92.9 grams piece of silver gray metal is heated to 178 degrees Celsius. So you write down what is given to you. You're given the mass of a silver gray metal, which is 92.9, and it is heated up to the initial temperature of the metal is at 178 degrees Celsius, and then quickly transferred to 75 milliliters of water initially at 24.0 degrees Celsius. So the mass of the water is 75.0 grams, in which this metal is transferred, the hot metal piece is transferred, and the initial temperature of water is 24.0 degrees Celsius. After 5 minutes, both the metal and the water have reached the same temperature. That is 29.7 degrees Celsius. So the final temperature of water increases and the final temperature of the metal decreases. So when it becomes equal, that is 29.7 degrees Celsius. That is the temperature when the heat has transferred from the metal to the water. And after that, the temperature equalizes. And so the final temperature of the metal and the water is the same. Determine the specific heat and the identity of the metal. So we need to find the specific heat of the metal. This is what we need to find. Now, here are a few things. First is we are given the mass. We are given the mass of the metal, and we need to find the mass of the water. But we are given the volume of the water, which is 75.0 milliliters. And we know the density of water is 1 grams per milliliter. So when you multiply the density with the volume, you get the mass of water. So you will have to do this transformation. So the mass of the water comes out to be 75.0 grams. So that's one piece. Second thing is the specific heat of water, which is 4.184 joules per gram degree Celsius. Okay, so this is something that is already known. So the density of the water is known, and the specific heat of the water is also known. So you're going to use that. Now, another thing is the final, the change in the temperature. The change in the temperature for water and the change in the temperature of water, and let me just change a different color here. The change in the temperature of water and the change in the temperature of the metal. That is T final minus the T initial. Again, the T final minus the T initial. So T final for the water is 29.7 degrees Celsius. T initial of the water is 24.0 degrees Celsius. So this change in the water is 5.7 degrees Celsius. So the temperature of the water increases by 5.7 degrees Celsius. On the other hand, we have the metal. The initial temperature of the metal was 78.0 degrees Celsius, and the final temperature is 29.7 degrees Celsius. So when you subtract, it becomes negative. Final from the initial is negative 148.3 degrees Celsius. So the temperature of the metal decreases and the temperature of the water increases. Okay, so we have now the change. We have found the delta T values. We have the masses of the metal. We have the mass of the water. We have the initial temperatures. And so we found the delta T value from there. We have the specific heat of the water, and this is the entity, the specific heat of the metal that we need to find. So we have all the other variables, but the one that is the unknown is the specific heat of the metal, which we are trying to find. So we are going to use the formula Q is equal to, that is the heat is equal to mass into the specific heat into the change in temperature. Now, keep this in mind that the metal Now, in this book, for some reason, the absorbing is considered to be a negative number, but in the OpenStax book, but in reality, the heat that is released should be a negative number because mathematically it comes out like that. So keep that in mind. It doesn't matter. Negative sign just shows where the flow of the heat. Okay, so here the metal is losing the heat and the water is gaining the heat. Okay, so we see that mathematically the level of the temperature of the water is increases and the temperature of the metal decreases. So anyways, here we have the Q is equal to M specific heat, and specific heat is also said as C in some of them. So specific heat times the delta T. So you're just going to plug in the numbers and do the algebraic transformation. So let's do this first. So let's put for the metals first. The weight of the metal is 92.9. So 92.9 grams times the specific heat of the metal, which we are trying to find, times the delta T value for the metal is a negative 148.3 degrees Celsius. And this whole thing is a negative number. Okay, and this is equal to the mass of the water, which is 75.0 grams times the specific heat of water is 4.184 joules per grams degrees Celsius times the change in the temperature is 5.7 degrees Celsius. So this is the way you will set this up. Now keep this in mind that when the brackets open, then minus and minus cancel out. So this whole number becomes a positive number then. This becomes a positive number. So we now have this arrangement, specific heat of the metal is equal to 75.0 grams times 4.184 joules per grams degrees Celsius times 5.7 degrees Celsius over 92.9 grams times 148.3 degrees Celsius. So when you set this up, you will see that degrees Celsius and degrees Celsius cancel out, and grams cancel out, and you are just left with the unit of joules per grams degrees Celsius, which is the unit for the specific heat. So here we will see the answer comes out to be for the specific heat of the metal. Specific heat of the metal is equal to 0.13 joules per grams degree Celsius. Now the question is that what is the identity of this metal? So here the metal, because if you compare it to the tables, we see that this metal is silvery gray, and this value of the specific heat is very close to gold also. But the question is saying, if we identify the identity of the metal, since it's silvery gray metal, so it's obviously not gold. So this is the specific heat. So the identity of the metal is, this is lead. It is close to lead. Okay, so that is the answer for 5.4. Now let's look at 5.5. Now 5.5 problem is relates to the heat produced by the exothermic reaction, and this is on page 249, 5.5 problem. Okay, so here we are looking at the reaction. So let's look at the reaction first. When 100 milliliters of 0.200 molar sodium chloride aqueous solution and 100 milliliters of 0.200 molar silver nitrate solution aqueous, both at 21.9 degrees Celsius, are mixed in a coffee cup calorimeter, the temperature increases to 23.5 degrees Celsius as solid silver chloride forms. How much heat is produced by this precipitation reaction? What assumptions do you make to determine your value? So here you write down the equation. and just make sure that this is balanced. So this is a balanced reaction. Sodium chloride is soluble in water, so it's aqueous. Silver nitrate is soluble in water, so it's aqueous. Then sodium nitrate is formed and silver chloride is not soluble in water, so this is solid. Now here we are given the volume. So write down the volume of sodium chloride solution, 100 ml, and the volume of silver nitrate, also 100 ml. So keep that in mind, that when these two are mixed, then the total volume of the reaction is equal to the volume of coming from the sodium chloride solution plus the volume that is coming from silver nitrate solution. So here we have 100 milliliters plus 100 milliliters. Okay, so that is the volume of the total reaction solution. So that comes out to be 200 milliliters of the volume of the reaction. Okay, then the mass of the reaction is equal to the density of water times the volume of the reaction, and that is equal to 1.0 grams over milliliter times the volume is 200 milliliters. Okay, and that is the mass of the reaction, and that comes out to be the mass of the reaction is equal to 200 grams. Okay, all right, now we are also given the molarity, which is 200.200 molar. The molarity of the silver nitrate solution also is 0.00 molar. We are given the initial temperature, which is 21.9, and the final temperature is 23.5. So the change in temperature is T final minus the T initial. So you have 23.5 degrees Celsius minus 21.9 degrees Celsius. So that is giving you the value of, okay, so that gives the value of the temperature 1.6 degree Celsius. And since the final temperature is a positive, is a bigger number than the initial temperature, so that means the heat is released. It's an exothermic reaction, and the positive change, delta T, is a positive number. Delta T is equal to change in temperature. Okay, so what is the heat of this reaction, the Q of this reaction? So for all, we will follow the formula that the reaction is releasing heat. Okay, so the heat released is, this is the heat released by this reaction. As you can tell that the final temperature is more. The solution absorbs the heat, and then its temperature rises, and that's what you measure, the rise in the temperature of the reaction mixture. Okay, so we will still follow the same formula, but we are going to make some assumptions here. What are the assumptions? The assumptions in these calorimetric problems are first of all, that the reactions, these are all aqueous reactions. So these reactions are occurring in water. Okay, so in the aqueous medium, the values of the water are used, the values for density and the value for the specific heat. So this is the reason why when I had the volume of the reaction mixture, and this volume was converted to the mass of the reaction using the density. Okay, density and the volume. So we have the density and the volume. Density and the density times the volume gives you the mass of the reaction. Okay, so you have the mass of the reaction coming off from the density, and then you're also going to use the specific heat of water in this reaction. And in the specific heat of water is 4.184 joules per gram degree Celsius. Okay, now keep this in mind that the heat that is given off by the reaction, that is the pure sodium, sodium chloride and pure silver nitrate, when those molecules, when their bonds break. So the heat that is released is absorbed by the reaction. So the solution, the water, okay, that's taken in. So M times delta S, H times delta T. So we will be using the specific heat of water in this case. So keep this in, this is for water. Okay, now we also assume that there is no heat loss. In other words, the calorimeter is not absorbing heat and there's no heat loss in the surrounding. So whatever heat is being released when the bonds are breaking and the new bonds are formed, that heat is getting trapped in the reaction solution, which is the water. Okay, so here the rest is just plug in the numbers. So the mass is 200 grams. 200 grams. That is for when sodium chloride and silver nitrate are mixed, 100 ml each. So, and then comes the specific heat of water, which is the 4.184 joules per grams degree Celsius times delta T. Delta T is 1.6 and it's a positive numbers. So times 1.6 degrees Celsius. And here you have the Q of the reaction. Okay, so, and then that's Q of the reaction because it's a heat is being released here. Okay, so here, when you multiply these, you get this answer. You get 1,338.88, and that is joules. Okay, so if you look at these units, grams and grams cancel out, degrees Celsius and degrees Celsius cancel out, and you are just left with the unit of joules. So that is the Q of this reaction. Okay, Q of the reaction, and this is also the Q of the solution. So same thing. Okay, but you can also transfer this into scientific notation. So we have here 1,338.88 joules. Okay, so now transfer 1, 2, and 3, the decimal, to a scientific form, which now becomes 1.33, and you can drop off, we can drop 8 and then round up 3 to 4. So 8 is more than 5, so round up 3 to 4. Okay, so times, we moved it 3 places, so this becomes 1.34 10 to the power 3 joules, and that is the heat of the reaction or the solution. It's the same thing. Okay, so that is the answer. Okay, now let's look at the next problem, which is 5.6, page 251. And here we are looking at the heat that is involved in the dissolution of KCl. So you have KCl, and KCl is dissolved in a sample of KCl, which is dissolved in water, and some amount of heat is involved here. Now, the mass of the KCl given is 3 grams, and it is dissolved in 300 grams of water, 300 grams of water. So what is the reaction? What is this total solution? The total mass of this solution or of this reaction is 303. So you add the two things together. Okay, so the question here is, when 3 gram sample of KCl was added to 3.00 10 to the power 2 grams of water in a coffee cup calorimeter, the temperature decreased by 1.05 degrees Celsius. How much heat is involved in the dissolution of KCl, and what assumptions did you make? So here we see the temperature has decreased. So when the temperature decreases, that means when the KCl broke up into the water, into its ions, that time it absorbed some of the heat from the water. So that's why we see a decrease in the temperature of water, okay, when KCl was added. So the change in temperature is negative, is equal to, so this, let's just put this here, is negative 1.05 degrees Celsius, okay? So we know the mass, we know the change in the temperature, and we are doing this in water. So the specific heat of water is equal to 4.184 joules per grams degrees Celsius. Okay, so that is for water. And we are going to use this specific heat. And the formula that is going to be used is, once again, Q is equal to M times specific heat times delta T. Okay, so we will use the mass, which is equal to 303 grams times the specific heat. The specific heat of water, 4.184 joules per grams degree Celsius, times the change in temperature was negative, times the change in temperature is negative 1.05 degrees Celsius. So remember, the heat itself cannot be negative. It's only the negative is just a direction of flow. So you can remove that. So here we have 1.05 degrees Celsius. Okay, so that is the total heat that is involved here. And now we are going to see that the grams and the grams cancel out. Celsius is cancelled out, and you are only left with the unit of joule. So let's calculate this. So the answer comes out to be 1331.1396. 1396 joules. And now the question is asking you to convert this to kilojoules. So get the value in Q should be in kilojoules. So is how many kilojoules? So here we know that 1 kilojoule is equal to 1000 joules. 1 kilojoule is equal to 1000 joules. So 1331.1396 joules times 1 kilojoules over 1000 joules, and that cancels out the joules, and you are just left with the kilojoules. So the answer comes out to be 1.33 kilojoules. And that is the value of Q, the heat that is involved in this reaction. So that's the answer. Okay, now let's look at the next problem, which is 5.7, and this relates to the bomb calorimetry. Okay, so bomb calorimeters are like closed, very closed containers, tightly sealed. So all the heat that is involved in this reaction gets trapped inside. And we also measure that, or it is the amount of heat capacity of the bomb calorimeters are also measured. So let's look at this problem, which is on page 253 and the problem 5.7. So here we are given benzene, that is C6H6. Benzene is organic compound made up of 6 carbon, 6 hydrogens. The mass of the benzene given is 0.963 grams. Okay. And when this benzene is burnt in a bomb calorimeter, the heat is trapped and there is an increase in the temperature. The delta T value is 8.39 degrees Celsius, and that increase. Okay. Now benzene is burnt and nothing is left. So the amount of heat that was involved is actually absorbed also. Some of the heat is also absorbed by the heat bomb calorimeter, and the heat, it depends upon the heat capacity of the bomb calorimeter, which is 784 joules per degree Celsius. Okay. Then this reaction is also there's some water is also evolved in this reaction, and this reaction in the water absorbs the heat also, and the amount of water, the mass of the water is, again, the volume of the water is given, the density of the water is known. So you take the volume of the water times the density of the water, you get the mass of the water. Because you need the mass, because you're using the formula mass times the specific heat times the delta T for water. So we are also going to use the values for the specific heat of water, which is 4.84 joules per gram degree Celsius. We already know the delta T value. And here we are also now adding the heat capacity of the bomb calorimeter, which is calculated, known, or is, given to you, and that comes out in this case 784 joules. So let's joules per degree Celsius. So let's calculate this now, putting these numbers. So here you have the mass of water is 925 grams times the specific heat of water is 4.184 joules per grams degree Celsius times the value of delta T is 8.39 degrees Celsius. Okay, so this is one piece. Now you add it to the heat capacity of the bomb calorimeter, which is 784 joules per degree Celsius, okay, times the delta T value is 8.39 degree Celsius. So when you add these two, this is going to give you the amount of heat that is released when benzene is burnt. So here, let's do this calculations. Okay, so when you take the mass of water, 925 grams, and you times the specific heat of water, which is 4.184 joules per grams degree Celsius, times the change in temperature, which is 8.39 degrees Celsius, you multiply all the three entities and you get 32,470.97 joules, okay? And on the other hand, you have the calorimetric, the heat capacity of the calorimeter, which is 784 joules per grams per degree Celsius, times the 8.39, which is the change in temperature. So when you multiply the two, you get 6,577.76 joules. And you add the two together, you get 39,048.73 joules. But the question is now asking you to calculate this in kilojoules. So we will take 39,048 times 73 joules times 1 kilojoules over 1,000 joules. So here, this cancels out the joules and you are left with 39,048.738. Divide that by 1,000 and you get 39. The value of Q comes out to be 39.04 joules. So just take one place after the decimal, kilojoules. And that is the answer. Okay. Now we have finished till problem 5.7 and we will stop here. And in the next video, we will look at the enthalpy calculations and then, just Hess law. Okay. Thank you. Bye-bye.